All right, so y'all did 1, 2, 3, 4, 5, or 1, 2, 3, 4, and it sounds like everyone did just fine. They're pretty easy. Has everything to do with the specific weight times the Z for pressure, right? Totally a function of the depth. So we wanted it down here, it's that depth. If we want it up here at 38, it's the difference. So one of the things the book does a lot of is has a starting elevation and an ending elevation. So you'll get that a lot. So it can be a little confusing as far as like what the actual depth is, because they give you these different elevations. They're not trying to have you incorporate altitude into the problem. It's just the way surveyors do it. They don't use 0. They use whatever the elevation is, and then the second elevation. And then you just have to subtract between the two to figure it out. So when we do water flow stuff, they do that a lot. You kind of see that in the example problems that they have in the book, like that thing right there, right? Where they say, hey, the elevation here is 550. So that's not a depth, right? And then the elevation here is 525. So you just got to do the subtraction between the two to get that depth. Okay, so just look for that. It can be a bit confusing. So no questions on any of these? You're good with it? Let's toss some numbers out. Like for number 3. This one. So what'd you get for the elevation Z? 82.5 -38. That's right though, right? So that's the elevation. So then we're going to take Z, and this is water. And used what for the specific weight of water? 62.5. Did they say to do that? Yeah, so I think, I think it's 62.4 for the baseline of water. What's that table have? And I know I used 5. Yeah, just slam the door. Ruth is here. Announcements. Ruth is here. She's not letting anyone in. So if you're late, you don't get to come. Yeah, they don't really, like the table doesn't tell you. I mean, I kind of saw the 39.16 degrees Fahrenheit. Like, why is that number in there, right? So 62.4, 62.5. I think, go ahead. 64?
Yeah, it doesn't really ever tell us.
Says the specific on page 20, it says the specific weight of water is quite uniform. The generally accepted value is 62.4.
Okay. So just start using that number.
Yeah. The generally accepted, except for Google, right? Yeah, 62.4. I'm okay with 62.5. I guess I'll need to give that to you on a quiz or an exam. So we use the same number, but the book is saying 62.4. And I think that one resonates with me. 62. I've never heard of the 64 number as far as using it, but whatever.
I might be an idiot. Because on the first side of my papers, I am using 62.
Yeah. Yeah, so I don't know. I mean, it is relative, right, to the altitude and the temperature. Anyway, what'd you get for your number, Brian?
2,781.25. 2781.
And that is PSF. We're doing number 3. We looked at number 3. 2781, and that's if you used what? 62.5. So the elevation is going to be 82.5 minus the 38, right? Because the top elevation is 82.5. And we don't know where this pipe goes. We just know this end cap is at 38 feet. So like when I drew it, I was like, oh, I don't really, I mean, doesn't go straight down, I wouldn't think, but it could, I guess, go straight down. I don't know.
Oh, 50 plus 38 is bigger than 82.
Yeah. Yeah, that's true. very true. Can't go 50 feet straight down and get to 38. So it must be off at some slope. All right. And then let's do the cylinder one at 1.75 in diameter. We don't need that. The water depth is 8.5 feet. So again, we're going to use the specific weight times the Z to get pressure, P. Specific weight we'll say is 62.4, since that seems to be the accepted value for the book. And that is pounds per foot squared. And a depth of 8.5 feet. That is number 4. What do we get for that one?
Mine was 531.25, but mine was 62.5.
So that's using 62.5.
I got 530.4.
And that's using 62.4. Okay. All right, perfect. So this is all about just finding pressure at a depth, right? I'll tell you. I guess if I don't tell you, you can give it to me in either. I mean, they're both legitimate pressures, the same pressure. It's just a different unit. So yeah, I'll try to remember to put that on the problem. And then you'll know. But if not, then just give it to me in whatever you want and I'll figure out whether it's right or wrong. So that's good. All right, let's do one more. Let's do that swimming pool one. Actually, let's turn those in. Let's make a pile here. Yeah, absolutely. I don't have, yeah, you can set that over by the homework if you want, Kyle. Turn the head of the forward, looking at the center pressure and force the dam shown. So we'll do. BC. Okay, perfect. Yeah, let's do the pool one, number 5, and then we'll expand it. So the swim pool shown below, determine the resultant hydrostatic force and location, and locate the center of pressure on surface A, B. Perfect. That's going to work us into this next part, which is total force. So I'm going to draw the pool real quick. Three feet, 5 feet, 12 feet, 8 feet. And it does say the width is 10 feet. So that must mean that I'm referring to it as like the depth, right? It's this dimension. That's better, right? Yes. Well, this is number 5. So what they're asking for is the hydrostatic pressure, hydrostatic force on surface AB and locate the center of pressure. So AB being this vertical surface, right? All along here. Everyone see that? All right, so what we need to know is we need to know what's the pressure at the top and what's the pressure at the bottom, and then we need to build the pressure curve. Okay, because that is not linear. I mean, it's linear, but it's not uniform, right? It goes from what's the pressure at the top? 0, right? There's no hydrostatic pressure at the top due to the water. What's the pressure at the bottom? So we just learned how to calculate that, so we can do that. I put little notations on like pressure at 8 feet, so I know what pressure I'm working with. That's going to be the specific weight of the fluid times the Z depth. I'm guessing this is water, swimming pool. $499.2. And the units are, this is cubed, PSF, pounds per foot squared. And how does water pressure act on a surface? All directions true if the water's all the way around. Perpendicular to the surface, right? So if the surface is at a slope, we're perpendicular to that slope surface. If the surface is vertical, then we're perpendicular this way. So that water pressure, I'm going to draw in as that right there. And that's the 499.2. So I'll stop it there. And it goes up to 0, right? So it's this water pressure curve. It's like that. And it doesn't just act on this edge, correct? It acts all the way across that surface. I can attempt to draw it 3-dimensionally. Ooh, got my angle's way off there. Yeah, I'm gonna be done here, but I think you get it, right? You get it. It's acting over that entire surface and the shape is triangular, right? So to get the hydrostatic force and the location of that concentrated load, how do we do that? Anyone remember from statics and strengths? Well, what's the concept? The concept, center that load shape, right? So for a triangle, it's that geometric center of the triangle. And then if it's 3-dimensional, then it's just halfway on the depth because it doesn't change, right? It's triangular the whole way. So we need to know like, oh, a triangle. How do we find the geometric center of a triangle? It was kind of down in here somewhere, right? The resultant. Yeah, it's like 1/3 and 2/3 is the location. How do we get the magnitude?
Like how strong it is?
Yeah, how big is this?
Oh, right in that spot. Well, we would have to find the difference between 8 minus how high up the
Area of the curve. Area of the load curve. So this area is how we get that, right? So since it's not just an area, it's a volume, we would find the area and then do what with it? Multiply it by the 10 to get the entire length. So it's just calculating a volume of the load curve. So remember when we had a load curve like this? How did we find the resultant? Area of the load curve, just this distance, 10 feet times this height, which is usually like, 60 pounds per foot type of thing. Right? We took the 60 times the 10 and we get 600, the feet cross 600 pounds. So that's how we concentrated a distribution in statics. We find the area of the curve. So here's our area of our curve. We're going to find that load first, right? But that's just the load on this one edge. And then we're going to multiply it times this length of 10, and we'll have the full volume of the load curve. Does that make sense? Then go ahead.
Would it be 8 times the 400?
What's the area of a triangle?
1/2 distance.
Yep. Yep. So it's going to be 1/2. Base is 499.2 pounds per foot squared. And I'm going to put my units in so I make sure I get this right. 8 feet. You could. I'm just going to do it individually. Yep. All right, so it's 0.5 times and then 8 times. So this gives me 1996.8. And one of those goes away, and that's pound per foot. And then we're going to multiply times the depth to get this total volume of load, 10 feet, and then that crosses. So another decimal point, 19968 pounds. Right, because we can get the volume from any shape, any two-dimensional shape, just by multiplying times its length or depth, as long as that shape doesn't change. And water's not changing, it's going to stay. So the 10 feet, that came from this depth, and it gave us that on the problem. So the width of this pool is 10 feet. So where is that applied? 19,968.
1/3 of the triangle and 5 feet over.
Yeah, so it's down here at the 1/3 this depth from the bottom, or 2/3 from the top, however you want to do it. And then halfway over. So it's like, I don't know, right in here somewhere. I am going to call it the resultant hydrostatic force. Oh. So I put it here, right? My angle's a little off, but. And then what do we get for the location? Like 1/3 of 8 would be 2.66 from the bottom, or 5.33 from the top. However you want to give it. 5.33 feet. That's what that sidewall of the pool is feeling. That's why we don't make pools out of sheet metal.
Did you get to 5.33?
So that's 2/3 of 8. So the way I do that is 2/3 is 0.666. 8 times 5.32. Rounded to 533. Yep. So for a triangle, it's 2/3 from the top, 1/3 from the bottom for that geometric shape. Good. Yeah, yeah. It's crazy. Amount of load gets generated. Yeah. Yep. I have one of those. They're definitely not 8 foot. Mine's 4 foot. So that's going to reduce the load quite a bit. Yeah. Yep. All right, let's do another one. Let's do surface CD. Yeah, surface CD. So I'm going to kind of redraw surface CD on a new piece of paper. All right, so we have it's 5 foot from here to here. 3 foot here. We know the pressure at the bottom, right? That's 499 point, what was it? 2? 499.2 pounds per foot squared. So now we need the pressure here at point D. Or at 3 feet. This is CD. What do we get for pressure at D? 187.2. Okay. So then what's our curve look like? We have a pressure here now. This is the pressure at D. Here's the pressure at C. And you want to draw them perpendicular to the surface. So that's here, perpendicular to the surface. And then create your curve. And just know that curve, has a depth of 10 feet. Or a width of the pool of 10 feet, right? So it becomes a volume of pressure. So the goal is to figure out that volume of pressure and then where that thing acts.
Pythagorean theorem to find that, right?
So yeah, there's a couple ways you can do this. To find the volume, you can actually just break it into shapes, right? Rectangle and a triangle. And that'll find it for you. They do have an equation for the location of the centroid in the book. So here is one here, right, that creates the trapezoid. And they say that y to r, this distance is this equation. Yeah. So you have to kind of read their notation, you know, and figure it out. Z1, Z2 is not too bad. Z1, Z2 is the depth here. Z1's the depth here. And then this, I believe, is their Ly. I think that's that, although their two symbols don't look the same, right? But I think that's got to be there. And then you can run this equation to find this y sub r distance, or the y distance to r. Should work whether this is straight or sloped, right? I would think. Yeah, here they set it up over here. Z1, Z2, there's that L distance. And this one uses a theta. So let's see if they give us that equation. Oh, they just kind of work their way through it. And they give it to you here with this slope. So resultant force and center of pressure for a submerged inclined plane surface. They work it out here to get the location of that force. So we can calculate the force, but getting the location is a little bit tricky with this shape. So I'll use this one, right? But we need F sub r before we can run this. All right. So go for the volume. Let's figure out that resultant force. And I'll do it also. So I'm going to do it just in these two shapes. You shouldn't, like, what's the rectangular shape? Oh, do you need an angle? Yeah. Can you figure out the angle? Yeah, you should be able to. So let's do it. Like, what's this distance here?
It's 187.
Yeah, it's that number. What's this distance here? 499. What's this distance? Did they not give you that? Oh, so we have to calculate it. Yeah, how do we get that? Yeah, we build a triangle and we say, okay, I know how far it is across the bottom. It's 8. I know how far it is vertical. It's 5. So we can get an angle here or here, wherever we want it, and we can get this length. Pythagorean theorem, right? I'll call it distance C. So C squared equals A squared plus B squared, because it's a 90-degree triangle, correct? Yeah, so C squared equals 8 squared plus 5 squared. C is going to equal the square root of that. Oh, turn your calculator on. $9.43398. Anyone get that? Okay. Now I can get the force due to the rectangle. Because I know this distance and I know the height of the rectangle.
What you wrote FR and then like for the force equaling something. What are those little tiny letters underneath the F?
Yeah, so this one I wrote REC, rectangle. Just trying to keep it straight of what I'm doing. So this is the force due to the rectangle. And I'm gonna actually multiply the 10 feet in here also. So that'll be the total force of the rectangle, right? The volume of pressure. So the force of the rectangle then I can do the same thing with the triangle and just add these two together. It doesn't give me the location, but it does give me the total force. Force of the triangle. That's going to be 1/2 the base, which is 9.43398 feet, times the height, and I need this new height of just the triangle. So it's not 499, it's 499.2 minus the 187.2. That's the height. And then I have 10 feet again. I get 14,717. So there's the rectangle, there's the triangle. We add those together, I get the force hydrostatic of this CD surface. Yeah, CD surface. Can we get that? 32. What'd you get for the triangle? Anyone? Adding these two? You're gonna take the rectangle plus the triangle, right? Rectangle plus the triangle, adding them. Because we want that full load curve. Huh? Yeah, got it. Yep. That's an easy one to forget. All right, let's see if we can figure out their equation for finding the location. So looks like a few things undefined there to me. So they say this distance up right here, right? Because here's our concentrated load. If we can find it on this 2-dimensional, then we know it's just 5 feet over 3-dimensionally, right? So they call this L sub R. So the resultant location. Oh, actually, it's this distance. That's L sub R. So it is from the tall side to the short side. So coming from here to the location of this resultant, this length location of the resultant, the equation they use is 1 over F sub R bracket F sub V, whatever we think that is, and then Y sub R plus W X W plus F sub H and X sub R. That's the equation they give.
What page is that on?
It's on page 33. Location of the center of pressure, equating the moments yields. So these are like pressure moments. Let's see where they get them. Nope, that's the whole equation. Oh, I sub R would equal it, or L sub R. Yeah, would equal that whole thing. So they derive it like on the page before, and they derive it from this. It's going to get complicated here. So here's our setup, right? We have the same thing, but they break it down into these H and V vertical components. So with the inclined plane, they calculate this H, concentrated load. They calculate this F sub V, concentrated load. And that's where these things come from. FV, FH. And these are little moments. So they're multiplied by Y sub R. That's a Y distance. And a X distance. So let's see if we see those. Yeah, so here's the X sub R distance. And here is the XW distance.
So we have W, right?
We don't have, oh yeah, we could get it easy
Is
enough.
that the number we just calculated?
No. Because that looks like it's a vertical force downward. Inclined plane surface with W, but this W is like the total weight, I'm guessing. Do we even use W? Yeah, we don't even use W in this.
Yeah, we do. It's right down the middle.
Oh yeah, we do.
What is figure 3.7?
That's what we're starting with.
Oh, there's a formula in there.
No, they're just, this is the setup of what we're trying to do. So this L and this L are the same, right?
Yeah.
So they just go from here and then say, okay, we're going to do it this way. We're going to do it as a vertical surface and a horizontal surface, and then they're going to combine it. So let's see what they get for W. Oh yeah. I think you're right, Brian. So they take the specific weight times the volume. That is what we calculated. They break it down into angles using that angle right there. Right? Interesting. So here's the individual pieces, at least the way they've come up with them. Right? So it's on this page right before that they solve these things out, like W is the specific weight times the volume. So that does have to be what we calculated, right? That's our 32,000. So we would need the vertical force, which we could calculate. And I think these are just these two-dimensional areas, which is very much like the last problem we did. And then this is pretty straightforward distribution to get that. So once we have all that, we have this already. We need that. And we have that. See this F sub R. What is that? Why do they show it twice? You see this down at the bottom? F sub R looks different than W. This is the one we calculated. I don't think we have W. Let's calculate W. Just see what if it's different. Let's use their equation right there. How could it be different? It's going to be the same.
Would you go back to the same? So it's
W is the weight of the water occupying the triangle space A, B, C.
so ABC is that triangle with WA.
A, B, C.
So we haven't found them yet. We haven't broken our surface into its own triangle.
Weight
Oh,
of
I see
the,
what you mean. Yeah, we have the top shape then, right?
we have that shape.
Yeah, that's what we did. We didn't do the bottom.
Oh,
Right.
that's weird.
I think what we
This
found-
shape.
Yeah, I think
Yeah, we found this volume.
right. And I think we found
Weight of the water occupying the triangular space, which they would have said area. Do they mean volume or the triangular area? Do they do an example? Yeah, they're gonna do 62.4 times 3 times 4 squared over 2, 1/2 base times height. Nope, that's not right.
yeah, that is. The 62.4 is the specific weight,
Yeah, I get that.
and then base times.
Yeah, exactly. That's what I want to know. Plane surface with length 4 feet and a width 3 feet is inclined at 30 degrees. So they have 4 feet, 30 degrees, and 3 feet. Length 4 feet, width 3 feet, 30 degrees. So this is the shape they're doing. And that's 1 foot below. Find the result. So then W is 62.4. 3 is that distance. Four is this distance. I square it.
Did they square the 4 because both the base and height of 4?
Well, they square it because of this formula to the left, but that's different than this statement, that's for sure. Like they give the equation here for W and they square L. So they say specific weight times the width squared over 2. Wow. And then they do sine cosine. Sine 30 cosine 30. That's how they get it. So they're using this equation. So it's definitely more than the area.
That was squared. Yeah, the L squared right there.
Yeah, and then sine and cosine. So I don't know about, I guess this statement doesn't really, the weight of the water occupying the triangle, this is more than just the area times the weight of the water. So we have to use this equation. Specific weight, width, that's our 10 feet, length, that's your length of your surface, over 2 sine and cosine to get that. F sub V, that's easy enough. That's this vertical one. F sub h, that's easy enough. This is the horizontal one. So that's this one and this one. These are just distances, y, x, and x. XW is here. So it is like compared to that triangle. And then F sub r is what we calculated. Wow, there's a lot to that. It's complicated. Questions? I think I get it now, though. Yeah, we have all of the pieces. It's going to take a while. I think it's a good homework problem.
Why don't we do it first? And then
All right, we can do it first. We have enough time, don't we? How long are we in here? Yeah, 30 minutes. We already have F sub r. So let's just do them in order. Let's get F sub v. I'm gonna draw a new picture. I'll write it right up on top. And then I'll try and write it out. So it's 1 over F sub r. And this is being recorded, so you could look at it. F sub v yr plus this w thing times xw plus fh xr, and that's in a bracket, and then there's a big bracket here. That. Mm-hmm. Yep. So I'm going to try and draw it here. So there's our slope. And then here is our two loads. So here is the the vertical, where this is F sub v, and X sub r, what they refer to as, they do call this horizontal. It's a horizontal surface. FH, because it's a horizontal surface. And then this is V, because it's a vertical surface. F sub V. So then they have W here. I'll write that W equation in a second, but then this is XW. So that's a distance. This is XR. I don't know why they didn't use XH there, but they didn't. And this is YR. And then we already calculated this load, right? And that is F sub R. So I think we got them all now. F sub R, F sub V there, W there. I need the W equation, which is specific weight XL squared. Is that right? Specific weight WL squared, WL squared sine over 2 sine theta cosine theta. And theta is defined as this upper angle. Yeah, this angle. Theta. Wow. So I'm not sure what this W is. Oh, that's, bet that's gravitational constant. Because it's a small W.
Width times length squared.
Do they show W as the width? Maybe that is.
Just assuming, right, isn't that the number that we're plugging in?
Here, let me look. Yeah, you're right. It is 3 width.
Yeah.
So this small W is width. Yeah, ours would be 10. Exactly. Yep. That's over 2.
That theta is the same as like the bottom.
I don't know what you're asking. This theta is the same as,
That's right here.
yeah, absolutely. Yep, we have 5 feet and we have 8 feet, correct. So we can get theta. And we have this length as 9.
9.433.
Yep, 9.43398. 9.43398 feet. All right, let's just start picking them off. Okay, this is driving me nuts. So I'm going to change this part. Perfect. Well, I don't know about perfect, but I keep moving it.
Start with W, yeah.
Sure, let's go for W. 62.4. Our width is 10 feet. Our, oh, thank you. And L is the length of your surface. So that's the 9.43398. And then we need the angle theta. $57.9946. So I just did opposite over adjacent and used arctangent.
Yeah, but theta's in the bottom left.
Oh, you're right. Theta's up here. So it should be 5/8. Good catch. Inverse tangent. 32. Straight up. Pretty close. Yeah. So then we need sine 32 cosine 32 for W. Yeah, that is very odd.
You say it's maths.
62.4. Two, 6, 4, 5. All right, I'll do it again.
In your W, when you wrote the numbers, you didn't put it over 2 and you didn't square it out.
Oh yeah, I did not square it for sure. No, I didn't square it. Anybody get a number?
Oh, what did you get? Oh,
12,000?
1, 2, 4,
Yep.
7, 9.
I got that also. I got 12478.85. I kept all of this.
I didn't keep all that. I kept all of it.
Oh, okay. So some rounding going on. All right, let's get, yeah, so I was looking at that. We have feet cubed, feet, and feet squared. So yeah, that just comes out to pounds. Let's get F sub V. That's the next one. W, F sub V, and F sub H. So F sub V here. So again, I would just do the rectangle and the triangle and add them together, right?
We know how far out they go.
How do we know that? What's this number here?
499.2,
Yep, 499.2. What's this number here?
187.2.
187.2. Yep. Excellent. So right away, we got 187.2 times this length, which is 5 feet. So that's the rectangle. Then we need to add to it the triangle. 1/2 the base, and the base is not 499.2. It's the subtraction of these two.
So is the 187.2 is that the distance of that little top section?
Yep.
Yeah, that.
Yep, absolutely. Pressure. Yep. So what do you get for F sub V? Oh, that's just the area.
We're doing the rectangle triangle thing.
Yeah. So that's not F sub V. I think I need to multiply by 10 to get F sub V. So
Would be good for the rectangle there.
for the rectangle, 936. For the triangle,
I got 9,360.
you multiply by 10
Yeah.
already? Yeah, so I haven't done that yet.
Oh,
Yeah, and I didn't do that here. This needs to be multiplied by 10. So it's going to be 17,160. But I'm going to do the triangle again. Yeah, 780 for the triangle. 17,160 before you multiply by 10. And then 17,160 once you multiply by 10.
How did you get the 78?
So do you get the 1,716?
No, I'm not sure how you got there.
All right, so the area of the rectangle
Oh,
plus the area of the triangle. So the area of the rectangle is 187.2 times 5. And then the area of the triangle is going to be that minus that for this distance. And then 1/2 base times height. I think that was 780, the triangle. Yeah. Yeah, if you multiply 10, then I just multiplied by 10 at the end. But this one was, the triangle was 780 and the rectangle was 960? 936.
And then F of B is pounds, you know?
Yeah, so once you multiply by 10, it'll be in pounds. So then what's F of H? That's an easy one. The pressure at the top is 187.2, and that length is 8 feet. Yep, for sure. $14,976. Everyone see where I got that? That's just that rectangle, right? This rectangle is F sub H. So then what's X sub R? Yeah, should be 4, 1/2 of 8. And then what is Y sub R? Oh boy. Oh boy. So I bet they give us a Y sub R equation. I'll see if I can find it.
Yeah, Y squared is 1/3 Z,
Where do you see it?
page 30.
Oh,
Oh, I can see what the 2 pages
Oh, yeah.
are.
Y sub R, 1/3 Z. And Z is the depth to the bottom. Wait,
From top to bottom.
wait.
Oh, that's for.
That's for a
page
vertical surface. Height, the pressure location of SOR is determined as centroid of a trapezoid, Y sub R. Centroid of a trapezoid. I think that's what we need. Centroid of, oh, we have a vertical surface. You're right, Ryan. You're good. Yeah.
It's not only, it's not a triangle, but the triangle would be 1/3.
So it does, that's what it says. Y sub R is 1/3 Z. Location of FR. Oh, the first one is a triangle. The second one is much more complicated. So Y sub R, can you see that? Yeah. L equals L sub Y. That is the vertical distance here over 3 bracket 2 Z1 plus Z2 over Z1 plus Z2.
That's simple after the Y sub R,
L
no, before that, right? before that.
equals,
Oh, that's
distance here. Like the Y length,
Okay.
5 feet. So it's going to be 5 feet over 3. And then Z's are, Z1 is at the top. Z2 is to the bottom, so it's the depth. So this is Z1. Yep, 3 feet down. And then this all the way to the bottom is Z2. So Z1 is 3 feet And Z2 for us is 8 feet. Cool. So cool. Complicated. I get 2.1212. Oh my. I think we have everything though.
We have X of W.
Well, we can get it. It's this distance X sub W.
Wait, what is Z1? Okay.
Well, then just do 1/3 of the 8, right?
Yeah, this is going to be 1/3 of this distance. Yep. So this is 1/3 times 8. And our resultant force was 32,377. So that's this F sub R. 32,377.42. Yeah.
This is taking up a whole page.
Yeah, it is. All of that, you know, we have to remember what we're doing. Like, what the heck are we doing? All of that to find out where this force is applied. Like, we have the force, right? 32,000. We just didn't know where it was applied. So this equation is just telling us where it applies
Like where it applies in one.
on that surface, on that huge surface. So I don't think they show a graph. Yeah, this is the only graphic they show of it here. Sorry, we're not quite done yet. That's all right. You can come in if you want, but we're not done. He's like, I don't want any part of that shit. It's this thing right here, right? It's this location based on this slope.
That's not even telling us the depth of it. I mean, we know that's just.
No, it just gives us the length up the hill, right? Yeah. Wow. All right, so I'm gonna write it out.
This is for L.
Yeah, this is for this length of the length to the resultant, I guess you would call it. Uh-oh, I hit some crazy button. Oh, no. Yeah,
We don't need the, wait, didn't you already give us the equation for? Isn't it 1/FR FB YR plus?
Yeah, the one at the top there?
Yeah,
yeah, I'm just writing it out with all the numbers in there.
okay, got it.
Yeah. Maybe I can get it all on. Yeah, kind of. So it's 1 over, I'm just gonna write it, not talk it.
R is 4.
It's half of it.
So then, how did we get XW?
That was here,
1/3 of Z.
1/3 of 8. 1/3 of this bottom length. Which I calculated as 266. Yeah, 266.7. Then, oh, did you say XR or XW?
I said XR first.
Oh, okay. Because XR is up here,
Yeah.
just, that's just 4. I think that's it.
Magic answer pops up the end.
Oh, God. Hopefully.
I did if you get the calculator out.
I'm like, what's our guess? Like, that should be what? For less than half a 9, right? So it should be like 4-ish. I don't know. Something like that. It's gonna be like right in here somewhere, correct? So this is 9.4, so it's less than that. So it's gonna be 4-ish. What do you get? Did you get a number?
Yeah, I got 2.15.
Huh? That's down there. I would guess it would be more than that, but I guess it's dependent on that angle, you know, like the angle would change that, it would slide it up and down. Same load curve would change it. So,
And the fact that
The-
the top of the triangle isn't the surface.
yeah, no, exactly. Yeah.
So
Interesting.
I guess if the top of that triangle was the surface, it probably would be.
Yep, that's exactly right, I think.
Is the same as like finding a composite centrally?
It is, except for the slope part. Like, it's definitely like finding composite centroid, but it's on this angle. So you can see as the angle goes flat, then we would just use trapezoid to locate it, right? So as it changes angle, then it slides that resultant up and down, even though the load curve doesn't change. Yeah, it's interesting. I don't see my inverse button.
I got 4.002. But I did this on my own, so
Closer to the number I was expecting. Uh-oh,
we all 3 have to think.
maybe.
I guess I'm struggling.
I get 4.002. What'd you get?
Yeah, 4.0029.
Wow. That load, 32,000 applied 4.002 feet up.
That 0.0040, what did you do wrong?
Did you
I divided 1 by 32.
1,000? And then 17,000 times 2. 12,479 times 2.667. And then 14,976 times 4. 14,000. Yeah, it would probably, I would do this a few times before I would. 14,93676. Is it 76?
Yeah.
Yeah, 76.
30 minutes.
We have a class that wants to come in. All right, so now you guys want to do one of these on your own. Oh, yeah, that's exactly what we want to do, huh? Let's do it. Which one? So the next one, well, not the next one, but let's do number 8. Very similar.
Number 8 in chapter 3.
Yeah, so it says determine the resultant hydrostatic force. I'll put it in the video here, so if you don't have the book, you can actually look at it. Determine the resultant hydrostatic force and locate the center of pressure on the face of the dam shown below. So it's from here to here. So 15 feet of depth. They give you rise and run, so that should help you get the angle right. Everyone knows how to do rise and run. Yeah, and it's at the surface, it's not at a depth. So it should be a little easier. So let's go for number 8 as our homework.
So then instead of, for that one, then when we're finding the Z, right? We're not gonna do that y over 3 times 2z1 plus z2 over.
Yeah, so you'll have to look at your pressure curve, right? Your pressure curve is gonna look a little different because it's gonna be 0 at the top, not a trapezoid.
Then we do.
Right?
Oh, sorry. It'd be 1/3 z.
Yeah. But it's at this angle, so draw your load curve off at this angle where it's 0 here. And you can kind of see this pencil sketched in load curve there.
Yeah.
Yeah. All right. Excellent. Good luck with that.
You said there's supposed to be a quiz thing related to.
It'll be